Hi everyone, welcome to the third part of thermodynamics. In the previous two parts, we have discussed in detail the introductory concepts in thermodynamics, first law, second law, their explanations, etc. And in this third part, let's deal in detail the thermochemistry part. The most important term in thermochemistry is heat capacity. We can define heat capacity as the quantity of heat required to raise the temperature of the system or a substance through 1 degree. So when you heat a substance and when its temperature is through 1 degree, the amount of heat required for this process is equal to its heat capacity, and it is denoted by the letter C, and this can be calculated by the equation C equals Q by T2 minus T1. So let T1 be the initial temperature and T2 be the final temperature. So C is equal to, we can say, Q by delta T. So this is the expression for heat capacity, and this heat capacity, just like heat, this is also a path function. So we need to specify conditions such as at constant volume or constant pressure in order to define this system. Okay, define the state. So heat capacity, we have two types: heat capacity at constant volume and that at constant pressure. First of all, let's see heat capacity at constant volume. We have already seen from first law expression that at constant volume, the heat change Q is equal to delta E. That means the heat transferred at constant volume is equal to change in internal energy. That is, from the first law expression we have delta E or dE equal to dQ plus dW, and we will substitute for dW, rearranging and substituting, so that you get dQ equals dE minus P delta V. dE equal to dQ minus P delta V, so that dQ equals dE plus P delta V or PdV. And since the process is at constant volume, the dV term will be 0 and the second term as a whole will be 0. So we get dQV equals dE. So we know heat capacity means it is the ratio of change in the heat transfer to temperature, change in temperature, that is dQ by dt. So we can say heat capacity at constant volume CV equals dE by dt at constant volume. Okay, so that is heat capacity at constant volume is equal to change in internal energy with temperature. In the same way, we can have heat capacity at constant pressure condition also. And heat capacity at constant pressure, that can be derived from enthalpy equation. We have the equation for enthalpy change, that is dH equals dE plus PdV. That is the constant pressure condition. And already we had the equation from first law, that is dQ equals dE plus PdV. That is from first law, or it can be written, written as dE equals dQ minus PdV. That is the exact expression for first law, dE equals dQ minus PdV. So when you substitute this value of dE in the equation for dH, you get dH equals dQ minus PdV plus PdV, and that will become dQ at constant pressure is equal to dH. So we can say that heat transfer, change in heat transfer at constant pressure is equal to enthalpy change, and since heat capacity at constant pressure Cq equals dQp by dt, we can write Cp equals dH by dt at constant pressure. So we got heat capacity at constant volume Cv equals dE by dt, and heat capacity at constant pressure Cp equals dH by dt. Now let's see what is meant by specific heat capacity. So here, as the name indicates, heat capacity at a specific condition, that is specific heat capacity, that is mass will be unit mass. That means the amount of heat required to raise the temperature of unit mass of a substance through 1 degree is called specific heat capacity. So we can write the equation as C is equal Q by m into dt. So the mass is specified there for unit mass of substance, a quantity of heat required to raise the temperature of unit mass of a substance. And if the mass of the substance, or if the amount of substance is specified as 1 mole, that means the quantity of heat required to raise the temperature of 1 mole of a system through 1 degree, it is called molar heat capacity. Okay, so usually molar heat capacity we call it as Cp and Cv at constant pressure and volume condition. We usually refer Cp and Cv, and that is nothing but the molar heat capacities. So the heat capacity of 1 mole of a gaseous system at constant volume is represented as Cv, and that at constant pressure is represented as Cp. Here we can see the relation between Cp and Cv. The Cp and Cv are related by the famous Mayer's relation, that is Cp minus Cv equals R. Let's see how that derivation comes. We know equation for Cp is dH by dt and that of Cv is dE by dt. So Cp minus Cv we can write as dH by dt minus dE by dt. Now from enthalpy equation we have H equals absolute enthalpy, H equals E plus PV, and this PV equals RT for 1 mole of a substance. So we can write H is equal to E plus RT. So when you differentiate this expression, you can write dH by dt equals dE by dt plus R into dt by dt. So it becomes dH by dt equals dE by dt plus R. And this dH by dt is Cp and dE by dt is Cv. So we can write Cp equals Cv plus R, or Cp minus Cv equals R. So this is the relation between Cp and Cv. Now the ratio of Cp and Cv, that is the ratio of molar heat capacity at constant pressure to that at constant volume, is denoted by a term called atomicity, and it is represented as gamma. So we can write gamma is equal to Cp by Cv. So this gamma value depends on the nature of gases. For monoatomic gases, gamma value is 1.67. For diatomic gases, it is 1.40, and for triatomic gases, it is 1.33. Now, after Cp and Cv, or after this heat capacity changes, let's study in detail the various enthalpy changes associated with a chemical reaction. So, enthalpy change or heat change, simply we can say, for a chemical reaction, the amount of heat evolved or absorbed during the reaction is called enthalpy of a reaction. So enthalpy of a reaction is denoted by delta H, and it is the amount of heat evolved or absorbed during a chemical reaction. And if the enthalpy of reaction under standard conditions we are referring, that means if the reactants are in standard state means the temperature and pressure are specified. Temperature is 298 Kelvin and pressure is 1 atmosphere. So under this condition, the enthalpy of reaction is called the standard enthalpy of reaction. That means enthalpy changes under standard conditions of 298 Kelvin temperature and 1 atmosphere pressure is called standard enthalpy of reaction, and it is represented as delta H0. So let's see the various enthalpies of reaction. First of all, let's see what is enthalpy of formation. So enthalpy of formation we can define as the enthalpy change associated with the formation of 1 mole of a compound from its elements. So when 1 mole of a compound is formed from their elements, the amount of energy associated, or the enthalpy change associated with that change, is called its enthalpy of formation, and it is represented as delta HF. So here are some of the examples of enthalpy of formation. First one, we have enthalpy of formation of carbon dioxide, then that of methane and water. So here also, if all the species are in their standard state, then the corresponding enthalpy of formation is called the standard enthalpy of formation, represented as delta H0F. So we can write delta H0F is equal to enthalpy of compound in standard state minus enthalpy of elements in standard state. So that is the equation for delta H0F. We know enthalpy of a reaction means enthalpy of products minus enthalpy of reactant. So since this is the formation of a compound, 1 mole of a compound, we can say enthalpy change equals enthalpy of compound in standard state minus enthalpy of elements in standard state. But we know by convention the standard enthalpy of elements is 0. So we can write delta H0F, enthalpy of formation of standard enthalpy of formation of a compound is equal to the enthalpy of the compound itself, because under standard condition the enthalpy of elements is 0. So we can write standard enthalpy of formation of a reaction is equal to the enthalpy of compound itself. Next is the enthalpy of combustion. So this is the enthalpy change accompanying the complete combustion of 1 mole of a substance in excess of oxygen. For example, heat of combustion of carbon. We can write the equation, the same equation we have written earlier for the enthalpy of formation of carbon dioxide. That itself is the equation for enthalpy of combustion of carbon. That means carbon undergo complete combustion in excess oxygen to form carbon dioxide. If oxygen is in limited supply, it won't completely combust, or it won't undergo complete combustion to carbon dioxide, rather it forms carbon monoxide. So when we say enthalpy of combustion, there must be an excess supply of oxygen in order to facilitate complete combustion. And for carbon dioxide, or for the enthalpy of combustion of carbon, the value is minus 393.5 kilojoule per mole. Now, enthalpy of formation values are mostly negative, but in some cases it can be positive also. But enthalpy of combustion value will always be negative, since we know a large amount of heat is released as a result of combustion reaction. So delta Hc value is always negative. Next is the enthalpy of neutralization. As we know, enthalpy of neutralization is the enthalpy change associated with the neutralization of 1 gram equivalent of an acid by 1 gram equivalent of a base in dilute solution. So this is the enthalpy change accompanying the neutralization reaction. Neutralization of 1 gram equivalent of an acid with 1 gram equivalent of the respective base. So when you write the equation, for example, neutralization of HCl with NaOH will give water and NaCl with the liberation of minus 57 kilojoule per mole of energy. In the same way, neutralization of HNO3 with KOH to give water and KNO3 releases an amount of energy which is also equal to minus 57 kilojoule per mole. So it is really interesting to see that the enthalpy of neutralization of all strong acids by strong base is coming out to be a constant, and the value is minus 57 kilojoule per mole. So let's see why it is so. Why the constant value, even if we take different acids and different bases. If they are strong, if the acids and bases are strong, then the enthalpy value will be constant and it will be minus 57. So in order to explain this, let's elaborate the equation. Let's write down the equation in the dissociated form. We know in the equation of HCl and NaOH, both are strong electrolytes and they undergo complete ionization. So we can write H plus Cl minus plus Na plus OH minus, giving H2O plus Na plus Cl minus. So we can the identical terms can be cut on either side. so that the net reaction we can write as H plus OH minus giving H2O. So with an energy change of minus 57 kilojoule per mole. In the same way, when you expand the second equation, H plus NO3 minus plus K plus OH minus giving H2O plus K plus NO3 minus. In this equation also, the net reaction is the combination of H plus and OH minus to give water. So whatever be the strong acid and strong base you are taking, the net reaction involved will be the combination of H plus and OH minus to give H2O molecule. So that is a constant reaction and it will have a constant delta H value, that is minus 57 kilojoule per mole. But the things are different if one of the acid or base is weak. That means, to illustrate this, let's take the example of neutralization of acetic acid. That is CH3COOH plus NaOH giving CH3COONA plus H2O. And in this case, we can see the enthalpy change or the amount of energy released is minus 55.5 kilojoule. Compared to the strong acid strong base combination, here less amount of energy will be released. So that means compared to strong acid strong base, some additional amount of energy has been utilized for some reaction. So this difference or this additional energy is being used for the heat of ionization of weak electrolyte. We know in order for neutralization to occur, the acetic acid being a weak acid, it should be dissociated. So in order for dissociating acetic acid, some amount of energy will be consumed and that energy is called heat of ionization of weak electrolyte. So we can calculate heat of ionization of acetic acid equals heat of neutralization of acetic acid plus 57 kilojoule, that is minus 55.5 kilojoule plus 57, that means 1.5 kilojoule energy is there. So there is compared to the strong acid strong base combination, there is a reduction in the amount of energy by 1.5 kilojoule, and this 1.5 kilojoule of energy is utilized for the heat of dissociation of acetic acid, the weak electrolyte. So these are the essence of this video. We have discussed about the heat capacity definition, heat capacity at constant volume, constant pressure, specific heat capacity, molar heat capacity, and also the enthalpy changes associated with various reactions such as enthalpy of formation, enthalpy of combustion, enthalpy of neutralization, etc. Hope it is clear to all of you. Thank you.